Okay, please work. Lord knows. Alright, guys. I bet you thought you weren't doing anything today because I'm not here. But you were wrong. You were very wrong. Oh, we're doing some math today. Absolutely. How could we not? Before we jump straight into all that, I've gone through the rest of the semester and I've looked at how much time we've got, and y'all are not lying. We don't got much time. So this will not work as 100%, will never change. It is liable to change, but this should be a pretty good representation of what we're doing for the rest of the year. Y'all are gonna go on this trip, you're gonna get back, we're gonna review, and I think we're disappearing for stacks. And when we get back from that, I'm giving you the test on graphing trigonometric functions. After that, two big new topics, and that's it. Once we get through those two big topics, fundamental trig identities and solving trig equations, once we get through that, give a test on that, we are going to straight review for this final exam. Pretty much the entire month of May should be dedicated to final exam review. So that should be generally what the rest of the class looks like. And one other thing, the assignment I have planned for y'all today, I'm not intending this to be homework on your trip. Please don't do that. What I want is for it to be practice of the material we're covering today. So I want you to work on it in class today, and I want you to bring it to class with you the next time I see you. Though not Friday. Friday we're just reviewing for the test. Okay, without further ado, let's do this. So we talked about inverse trigonometry before. This is all that fun stuff with the negatives in the trig functions. There are 6 of these. Let's see, tangent, and then all the weirder ones. Let's see, cosecant, secant, and cotangent. I've had you use these a little bit to solve some right triangles. Now I want to really look at the details of them, figure out what makes them tick, and use them to simplify some expressions, which we will also use the unit circle for, which is why we got it over here. Okay. Unfortunately, before we get into the math on this, we got to talk about some silly notation things. So this -1 notation is one of the common ones. This is what most people we use. Another extremely common one for this idea of an inverse trig function is putting the word arc in front of it. So you could have arc sine of x. That means the same thing as sine inverse of x. You can have arc cosine of x. That's equal to cosine inverse of x. And the same is true all the way down. They're just different ways of writing the same thing. Now, up until like a week ago, or whenever I was making this lesson plan, this is all I had ever seen. I didn't know there was another way to notate this stuff at all. Until I opened your book, and I saw some extremely cursed information before my eyes. Your book uses the following: capital sine inverse of x, capital C cosine inverse of x, capital T tangent inverse of x. I'd never seen this in my life. I'd never seen it at all. I had to go to Wikipedia. Apparently this is a more obscure notation that is meant to make just what these are more distinguishable. We're not going to worry about all that. We're going to sum that up very simply. All you need to worry about is how to actually use these. I don't need you to worry too much about this capital letter. The capital letter does have some math definition things tied to it. It's not there for no reason. However, it just plays no role in actually calculating the value. And I'm a math major. I've been my whole life not even knowing this was a notation that existed. So if I got through okay, y'all will too. So we're not going to stress too much about these capital letters. You see the capital letters, they do it with the arc cosine too. In arc tangent and all that, they'll write stuff like this. It honestly looks ridiculous. But just treat it as if it were lowercase. It does not affect the solving of the problem at all. Okay, so all of this is just notation. so you recognize what it is we're talking about here. I'll try and wait a little bit here so I can write this down. Well, I guess it's a video. Pause the video if you need to. Okay, let's see here. What else we got? We covered the notation. The notation is obnoxious. But once you get through that, we get to the good stuff. Now let's actually start looking at these. All right, first let's look at sine inverse of x, or arcsine. As for which one I generally use, honestly, I go back and forth pretty often. Definitely recognize both. If I had to pick one, I'd probably go with the sine inverse of x with the -1, because that's what's on your calculator. Okay, so let's see what this looks like here. I want to show you what this looks like. Okay, here, so we got a 1, we got a pi over 2, -1, and a minus pi over 2. Lovely. Okay, so this function is going to look something like this. Let's see, I got to make sure I curve it through the origin properly. Okay, looks roughly like that. Now, I'm not going to make you graph these. We are done with graphing for the semester after I give you your trig graphing test, obviously. I just want you to have a visual of this. What I really want you to take away here, the big important information, is the domain and range. Now, I'm not going to make you memorize the domain and range. I'm not going to do that. I think that would make this very much not fun very quickly. We're not going to do that. However, you're going to need that domain and range to do any problem involving inverse trig. It's a requirement. So I need to be thinking about these when I'm doing problems. The domain of this guy is -1 to 1, and the range of this guy is minus pi over 2 to pi over 2. And remember, just very quick refresher on what domain and range are. I'm not going to make you analytically find it. I'm not going to make you memorize it. I'm not going to make you do any of that. All I need you to understand about domain and range. The domain is all valid x values in my function, and the range is all valid y values. So as a simple example, this function arcsine of x takes in values for x in between -1 to 1. I can plug those numbers into this function. I'm allowed to plug those in. And what it will always give me back, what it will always spit out, is a number in between -pi over 2 and pi over 2. That's all I need y'all to understand about this, is that this just represents a range of numbers that are allowed, so to speak. Domain are allowed values for stuff I can plug in. Range are allowed values for stuff I can get out. That's important. Okay. That's generally it for arcsine. I do want to write one sentence here that is succinctly explaining what this function does. Okay? So if I plug a number into this thing, it is going to give back a value, maybe I should say gives back, between -pi over 2 and pi over 2. And of course, it can help to be familiar with the decimals here. I'm not going to ban a calculator for this unit, so you don't need to memorize it per se. I think this is roughly like -1.57, this is like 1.57. Just as long as your value falls in between those, you're good. Okay, that's all for arcsine. Now let's see it in action. Okay, number 1, we're going to evaluate each expression in radians and degrees. Okay, part A is going to be the sine inverse of 1/2. Okay? Okay, another go around at number 1 here. Made a lovely mistake the first time. Okay, number 1 here, evaluate each expression in radians and degrees. Excellent. All right, I would like to evaluate the sine inverse of -1/2. Okay. To get started with this, I want you guys to train your brains to turn these inverse trig function questions into just straight up normal English, so you understand what you're trying to do. For this one here, what this is telling me, what it's telling me to do, is the following. Well, really, it's more asking me a question. It's asking me the following question. Where on the unit circle is there an angle with a y-coordinate of -1/2? That's what it's asking me, okay? No, that's not too bad, that's not too bad. And to be clear, let's just go ahead and get this out of the way now. This is pretty bad if you have to have literally everything memorized, if you have to have the unit circle memorized and all the domain and ranges. This is terrible. I'm not going to do that. I will give you a copy of the unit circle and I will give you the necessary domain and ranges. On the homework though, they don't specify those domain and ranges, so you need to remember to look for those. But on any test, I will give you that information. Okay, but let's put it into practice here. All right. So looking for a y-coordinate of -1/2. All right, let's do that real quick. That shouldn't be too bad. I've got one right here. That's nice. Okay. Let's see, any other -1/2s? Ooh, I got one right here. Okay. So this might not mean much to you non-math major folks, but essentially, an inverse function outputting the same value for 2 different inputs is a problem. It creates some mathy problems, so to speak. Because of that, this is why domain and range comes into play. This is why it comes into play. I need to choose one of these, essentially. I need to have a rule that tells me, okay, this will always come out to just one answer, no doubt about it. The way we take care of that is with domain and range. For this question in particular, since I'm trying to figure out what this whole thing equals, I'm looking for the output, then I need to care about the range. So the range of sine inverse of x is -pi/2 to pi/2. Okay, so the answer I get out needs to be in between those two things. All right, and I think this is a lot easier to visualize with a picture. Here's a picture, here's pi/2, positive pi/2, here's negative pi/2. Remember the negative, all that means is you just, instead of going right, you go left. All right, so if I need my answer to be within this range, in between negative pi/2 and positive pi/2, then it can be anywhere here and anywhere between this and pi/2. So anywhere here, any of this business here. Quadrants 1 and 4. And that gives me my definitive answer. 7 pi/6 is in quadrant 3. That is very much outside this range. So I disregard him and I take what is kind of a nerdy way called the principal value of this inverse trig function, which is 330 degrees and 11 pi/6. Now before I write that down as my answer and I call it a day, I need to be careful. That range is sneaky, guys. It'll get you. It'll get you in weird ways. I'm in fact not done. And it is entirely because of this range. Okay, so these guys are definitely in the right quadrants. That's not the issue. The problem is the path I take to get there. With 330 degrees, that's a positive angle. That means I start here and I turn all the way around to get here. Notice I had to go through quadrants 2 and 3 to get here. That's a problem. That's a huge problem. When you're really caring about the details of math, that's not allowed. You can't just travel through a region of numbers that break your function. You can't do that. It's banned. Can't do it. That's okay though, it has a surprisingly simple fix. Instead of going this way around, just start, oh no. Just start here and go left instead. Clever trick. Now, if we're going left, I reckon my answer's gotta be negative, and it will be. This is gonna be, and notice here guys, I'm going from 0 to 330. There's 360 degrees total. So if I went from 0 to 330, then I traveled 30 degrees. I went to the left, so it is negative 30 degrees. And for the radian measure, to some of you, I think this will be kind of just obvious, others maybe not, that's okay. There's a couple different ways you can think about it. It's gonna be negative pi over 6. Okay, that is going to correspond to the positive value right here. So a kind of trick you can do is just look at the degree measure, pretend it's positive, that radian measure is the same for the negative version. Or you could just convert it using the conversion factor. However you want to think about that part, by all means. But yes, I do need to make sure that I'm not traveling through banned regions. Can't do it, it's not cool. All right, we're gonna look at part B and C, but I'm gonna cut this clip short. Okay, part 3, parts B and C of number 1. Let's do it here. These are a little quicker, actually much quicker. These are kind of meant to be more specific examples here. On part B, the arc sine of 0.75, okay. What's going on here? I'm still being asked the same kind of question, but 0.75, 3/4, that is not on the unit circle. It's not. So in any case like that, where you get a value that's not directly on the unit circle, that's a calculator question. We can work with that. I got no issue with that. So this would go straight into the calculator. Now the value you get is going to depend on radian or degree mode, all that good stuff. And as to where it's located, I don't think any of your calculators are going to explicitly say arc sine, arc cosine, or anything like that. They're going to use the -1 notation like that. And hold on, let me just grab my TIA for it real quick. Never mind, I left it at home. But if you hit, I'm going off memory here. If you hit second and then you hit regular sine, you should get sine inverse. Same for all the rest of them. Okay, but yeah, this is not on the unit circle, so we just plug this in the calculator. If you do it in degree mode, then you will get 48.6, and for radians, you're gonna get 0.848. Lovely. So yeah, nothing too crazy there. That's just to make sure you know where the button is on your calculator. All right, part C is even quicker. So I'm just gonna write down the answer first, then talk about why. This one is undefined. Okay, so this has something to do with domain and range. Before on part A, I had to care about the range because I was interested in the answer to this thing. I wanted to know what came out. Okay, I'm interested in that here as well, but there's a problem with the number that's been plugged in. There's a problem with my input this time. If I'm caring about input values, well then I'm caring about x values, and I'm caring about the domain. I have to worry about the domain. So I'm gonna write down the domain of sine inverse real quick. That domain of sine inverse, oh, please tell me I wrote it down. Yes, I did. Is -1 to 1. So the only numbers I'm allowed to plug into this thing are numbers in between -1 and 1. Those are the only ones I'm allowed to do. -1 itself, 1 itself, and everything in between. But that then explains why this is undefined. We plugged in pi. Pi is bigger than 1, which means it is not in the domain. Anytime that happens, if you plug in a number that's outside the domain, and this is true not just for sine inverse, but cosine inverse, tangent inverse, any of those, if the number you plug in is not in the domain, undefined. Easy peasy. You just gotta remember to watch out for those domain ranges. And Lord knows I'll stress so hard. Please do not panic about that part. My goal with this is not to make you memorize 6 domains and 6 ranges. I will give you that information. Please just remember to refer to that information when you're working through problems in the book, because they are not going to explicitly remind you of it. They're not. Okay, that takes care of number 1. Let's look at the other inverse trig functions real quick. And I think we'll cut that clip right there. Okay, we took care of inverse sine, now let's take care of inverse cosine and inverse tangent. So let's do cosine first. Okay, so cosine inverse looks like this, or this, arc cosine. It looks like the following. Let's see what we got here. We got a 1 here, we got a -1 over here, we got a pi up here, and that'll do it for this one actually. We're gonna have a local maximum here, and a local minimum here. Oh, I didn't make that look very nice. Oh, right, yes, it has a point kind of in a strange spot like here. So it does this weird kind of very slow crawl up, flattens out a little bit, and curves. Oh no, not that much, not that much. Curves a little bit up like that. There we go, that's not half bad. Okay, that's our inverse cosine. Our domain of this bad boy is, let's see here, -1 to 1, and the range is 0 to pi. Okay, okay. Not too bad, not too bad. Right, and what this function is going to do is return a value between, well, let's see here, between 0 and pi. Oh, I guess I should say returns. Okay, that's all the info I need about inverse cosine. Now let's do some problems with it. Let's do some problems. Cut that. Okay, so let's look at number 2 here, parts A, B, and C for inverse cosine. Inverse cosine. All right. So very similar to before, for part A, when I'm evaluating one of these, I want to think about it in terms of a question. Here, though, I have cosine, so I'm interested in not y-coordinates. Before, I was doing y-coordinates because I was using sine. Here, I've got cosine, so I'm going to be looking at x-coordinates. So the question I'm interested in here is, where on the unit circle gives -√2 over 2. That's what I'm looking for, okay? Now I need to do that while taking into consideration the range of the inverse cosine. The range of inverse cosine is 0 to pi, so it has to be in between 0 and pi. So it can be here, and all in there, stopping here, nowhere else. So within that region, looking for x coordinates of -√2 over 2, smack right there, easy peasy. So that's going to be these measures here, 135 degrees, or 3 pi over 4 radians. Not too bad, not too bad. Okay, part B is very similar, very, very similar. In fact, the only thing that changes is the number. So the question being asked here is, where on the unit circle gives 0? Same domain, not domain, same range restriction, excuse me. So if I come over here looking for zeros, okay, well, I don't see very many of them, to be honest with you. I see 1 right there for the x-coordinate. Remember, it has to be an x-coordinate. It can't be this or this. Those are y-coordinates. If it was arc sine, I'd care about that. But I've got arc cosine, so I care about x-coordinates. Right there. So my answer are these two guys. 90 degrees equal to pi over 2. Nothing too shabby there. C is also really fast. This is another calculator test. It's located like right next to inverse sine. Oh, I forgot to say earlier, but yeah, Grace and Summer, you're on your own for this one. I have no idea. I'm sure it's on there somewhere. Look, dig around and find it. This one here is just another type in the calculator problem. 1/4 is not in the unit circle. So if this goes on our calculator in both modes, that's another thing, Grace and Summer, that you need to remember is how to swap between the modes on that stupid, stupid machine. Okay, so yes, if we do that, we're going to get, let's see if I can read my handwriting, 75.5 degrees, and, oh gosh, 1.318 radians. All right, magnificent. So very, very similar to inverse sine, except now I'm looking for x coordinates. X coordinates. Okay, let's look at inverse tangent. Okay, let's get inverse tangent going here. This will be the last big one we look at, and then we're going to look at some cool compositions of these things, and we will be done. Okay, inverse tangent. The tangent inverse, or arctan of x. Beautiful, beautiful, beautiful. All right, let's get a visual going here. If we do that, we'll have pi over 2 up here, minus pi over 2 down here. And now this one's interesting because it has some asymptotes. We briefly talked about the vertical asymptotes before. These are slightly different. These are horizontal asymptotes. That just means they go side to side, so up and down. Right, and you don't got to remember anything else other than that. They're just present. Our graph here is going to get closer and closer and closer to these dotted lines forever, but it will never cross. Okay, so it does pass through the origin, and it curves up nice like that. And I don't want to mess this up. Like that. I messed it up. Wow, that looks real bad. Let's see if I can't fix that. I'll tell you, Okay, my domain for this bad boy is actually going to be all real numbers, which is great. So that basically means you can just plug in anything. I'm going to write it all fancy, because I can't resist. I'm going to say it's negative infinity to infinity. All real numbers. That's nice. I'm allowed to plug in anything. Don't have to stress too much about tangent, or arctangent, excuse me. Okay, the range of this is minus pi over 2 to pi over 2. And, okay, we've seen that range before. We've seen those numbers. But here I use parentheses, and before I use brackets, okay? So I got to dig in your memory banks a little bit here, like literally back to the first week of school when we talked about this stuff. The brackets like this mean inclusive. The parentheses like this mean exclusive. So the version of this with the brackets means I'm allowed to get positive pi over 2 out. With this version, the exclusive version, I am not allowed to get pi over 2 out. So it excludes the endpoints. Excludes the endpoints. And yeah, besides just understanding that this means a bunch of numbers in between these two things, I don't need much more than that. I just need to understand that. Okay. Oh yes, I almost forgot. This will return a value within minus pi over 2 to pi over 2, and I'll just note here that that is exclusive. Okay, so now let's look at some problems real quick. Excuse me. Okay, here we go. Inverse tangent problems. So very similar to before, we got parts A, B, and C. Let's go through them here. Okay, inverse tangent of 1. Same as before, I want to turn that into a question my brain can more easily understand. This is asking me where on the unit circle gives a tangent of 1. Okay, that's what I'm interested in. And now this is a little trickier than sine and arc sine and arc cosine. With those, we can just go through here and we can just look for the digit. We just look for it. No real math going on there. With arctangent, I do have to do some calculation and I have to think about it a little bit. Now, I'm not going to lie to you. It is completely possible to remember all the tangent values for the unit circle. If you want to, I salute you. Go for it. However, I don't have them memorized, and I won't require you to either. What I will have you do is use your noggin. We're going to look over here and see if we can't figure that out. Okay, so of course I do need to remember the range of this guy. The range of inverse tangent is the following. Negative pi over 2 to pi over 2. So that means I have to be in either quadrant 1 or 4, and I'm looking for where I get positive 1. Okay. Let me sketch a little picture down here. All right. Minus pi over 2 is here, pi over 2 is here. So my answer lies somewhere in here, from pi over 2 all the way to pi over 2. Negative pi over 2, excuse me. Okay, so if I need a positive 1, then use your head, guys, use your head. If I come over and look at quadrant 4 here, this is positive and negative, positive, negative, positive, negative. No matter how I divide those, I'm gonna get a negative number. That's just how it goes. I mean, I can't make that positive, no matter how hard I try. So that eliminates quadrant 4 from the running, and it's gotta be up here. And in fact, it's gotta be pi over 4 right here, because these are the same digit. Don't forget, y'all, that tangent is calculated tangent is found by calculating y over x. So the way to test this, to see if I've got the right spot, is to take my y and divide it by x. It better give me what's in these parentheses. If it does, I'm golden, I'm good to go. If it doesn't, well, I'm out of luck. Okay, so let's check here just to make sure. I'll write it down here. So root 2 over 2 divided by root 2 over 2. We'll keep change float. We'll cancel diagonal factors, and we just get 1. Beautiful. That makes that nice and simple. So this is 45 degrees, or pi over 4. So yeah, in my opinion, arctangent is a lot more fun. It's a nice little challenging puzzle. I like it. Okay, let's see if we can play that game with the arctan of minus root 3. Okay? Same range. So I have to keep that in mind as well. Okay. So let's see here. Minus square root of 3. How am I going to go about thinking about how to get that to pop out? Okay. So I'm going to try and translate what's going on in my head just out into words so you can see how I think through this. All right. I'm looking at that. Honestly, I have no idea what the answer is. So I come over here and I try to figure it out. I know I've got a negative number there. All these are positive, so it ain't going to be up here. It's got to be down here because I got negatives in this quadrant. Okay? I'm gonna take a shot in the dark here and say it's not this one, because I mean these are the same digits, just one is negative, so I'm gonna get negative 1 if I divide those. It's got to be one of these two. Got to be one of those two. Okay? So if I test it at 300, and to be clear, like I'm not saying I know for sure this will work, I'm just saying, okay, it's probably not this one. Let me check these two, see if it works. I'll try 300. All right, so to do that, I need to take my y-coordinate, negative root 3 over 2, and I need to divide it by the x-coordinate, 1/2. If I compute this and it gives me negative square root of 3, I'm good to go. So this will give me negative square root of 3 over 2 times 2 over 1, cancel these, and sure enough, I found what I'm looking for. Though I maybe shouldn't have boxed that, might have been confusing. That just does, in fact, verify that I have the right spot. So let's see here. That was down here at 300. But don't forget, y'all, that same little weird trick that arc sine was playing on us, it's playing on us here too. I'm not allowed to go outside of the range. Like if I start here and I go the positive direction, all the way around to 300, I cross through these two. That was bad, I can't do that. So I just do the simple negative trick again. I start at 0 and I go this way 60 degrees to land here. And so I say this is negative 60 degrees, which is negative pi over 3. So yeah, lovely. All right, and then our last quick little calculator question here. Again, this is just to make sure you know where the button is. If you punch this in your calculator, you will get 0.9425 and 54 degrees. All right, so those are our basic problems here. I'm going to show you some slightly complicated more questions now. Let's do it. Okay, guys, let's look at the crown jewel for today, the trickier stuff. All right, so with these trickier problems, it actually uses something we've looked at before. When we were solving our right triangles with inverse trig, we would get down to a point where we maybe have something like this. We'd have, oh, I don't know, maybe sine theta equals, oh goodness, I don't know, square root of 3 over 2, something like that. We'd work through our problem and we get down to this point. And I'd go, how do you cancel the sine, guys? How do you do it? And you'd tell me, you'd use inverse sine. You take sine inverse of both sides. These cancel and you get your answers. Theta is the sine of root 3 over 2. I don't know, just a random simple example I made up there. The part I want to highlight is this right here. I took the sine inverse of both sides and I used that to cancel out my regular sine. Okay, like 95% of the time when you do stuff like that in math, you're allowed to just do it and not think about it. But you are kind of supposed to think about it and care about it, because funny things could be happening with the domain here and the range. And so what I've done is I've typed up every single possible case of objects like this where you could potentially cancel something, and I've shown you when you're allowed to do that. I'm gonna write one sentence here, but I've got all the math rules printed out on a sheet. I'll have the sub pass that out on the day I'm gone. Okay, so where was I going with? Oh yes, let me write this sentence. So I'm allowed to do this cancellation. So I'm gonna say, when am I allowed to cancel? Well, you're allowed to do that when your x value falls within the domain of the inside function. Okay, that's why I have all this printed out on a separate sheet of paper. Definitely keep up with it. This is a god tier cheat sheet. It's super handy to have around, to be able to pull out just like that. The way it applies here on my random example, my quote unquote inside function was the regular sine of theta. It's just the one that's the most inside, okay? So the way I would check to see if I could do that cancellation myself, if I was given this problem independently, is I'd go, okay, I'm gonna check my trusty table of domain and ranges. The domain of sine theta is minus pi over 2 to pi over 2. And the square root of 3 over 2, I know these are in forms where it's not maybe super obvious, but you can check with a calculator that goodness, I apologize, I had a brain fart there. Yes, so you can check that the square root of 3 over 2, I think it's about 0.866. You can check that that does fall inside this range. That's allowed, so I can cancel out like I did there. So yeah, whole bunch of lovely rules for that. I've got it printed out on a separate sheet of paper. Okay, now let's look at the good stuff. Okay, what question is this? Gosh, I have no idea. I need to go to sleep. This is number 4. Okay. We're going to evaluate. We're just going to straight up evaluate. We do not need any more direction whatsoever. We're just going to number crunch. All right, part A here. This is going to be the sine inverse of 1/2. Okay, so these are designed to look terrifying. Utterly, utterly terrifying. But don't worry, it's not bad, I promise. You may notice this is a potential candidate for some cancellation. I've got regular sine and its inverse. So I could potentially cancel this if there's no funny domain business. Okay, so let's verify that I'm allowed to do that. My inside function is sine inverse, okay? The domain, yep, there it is. The domain of sine inverse is -1 to 1. 1/2 is in between those, falls right smack in there somewhere. So that means I'm good. I'm good to go. I'm allowed to cancel this out. And so guys, I'm done. This is just 1/2. Oh yeah. So yeah, this can be really easy and quick in a lot of cases. Okay, so let's look at part B. Okay, the tangent inverse of the tangent of -45 degrees. Okay, let's run part B back real quick. I'm in dumb mistake. Okay. All right, part B. Tangent inverse of the tangent of -45 degrees. All right. So I should always look for potential candidates for cancellation. Here I've got inverse tangent, here I've got regular tangent. So this could cancel as long as my domain is okay. All right, my inside function is the tangent, regular old tangent. The domain of tangent of x is -π/2 to π/2. And -45 is in fact within that range. Don't forget, guys, -45 would be like here, like right here, and that does fall within this domain, because that domain is everything here, all in here. So right there is totally okay for the domain of tangent. Okay, and so I'm allowed to cancel. I just cancel those away, and my answer is -45 degrees. And on this one, guys, I am going to show you another way you could do this. I've run into people like this before who just like really don't like this cancellation stuff because it's annoying to deal with all the domain business. You can get around it. The way you do it is kind of just order of operations, like start on the inside and work your way out. So I'm going to show you this just in case this works better for somebody. So let me work this from the top. Okay, so instead of doing it this way where we cancel these out, I could start on the inside and calculate the tangent of -45 degrees. I could do that, okay. That just means I need to come to -45 degrees and then calculate the tangent. So y divided by x. So I need to divide -√2 over 2 by √2 over 2, and I'll let y'all check that that's -1. So this part right here, I should do a different color. The tangent of 45, I just found was -1. Okay, so now I have the tangent inverse of -1. But now you can see why the cancellation is kind of nice, because it's just asking me for what I had before. Where in the unit circle do I have a tangent of -1? Well, right there. So it's just -45 degrees. So yeah, Either way you'd like to think of these, go for it. I will not require you to do it a certain way. Okay, that takes care of part B. What was part C? Part C. Oh, yes, part C. Okay, we got the arc cosine of the cosine of 5 pi over 3. Okay, so got another candidate for cancellation. Got inverse cosine on the outside, or regular cosine on the inside. But I gotta check the domain. Yeah, check that domain. Oh man. Okay, so my inside function here is regular cosine. The domain of regular cosine is the following. Well, let me see here. It's going to be 0 to pi is 0 to pi. And you can pretty quickly check by just like using your eyeballs that 5 pi over 3 is way after pi. And so that is not in the domain. That's not in the domain. It's no good. Nonsense. So I can't cancel. This is very important. It is very tempting when doing these to just go through and just start crossing stuff out left and right. Don't do it, you're only gonna get like half of them correct. Because 5 pi over 3 is outside that domain, I cannot do that. And I have to do what I did here. It'll work from the inside out. So let's do it. First, I need to calculate the cosine of 5 pi over 3. That's easy, that I can do. I just come over here to 5 pi over 3 and take the x-coordinate. So, this right here, I'm going to recopy just for the sake of it looking nice. We know this is going to equal now the arc cosine of, well, the cosine of 5 pi over 3 was a half. All right, beautiful. Now I just want to calculate the arc cosine of 1/2, or in other words, where on the unit circle do I have an x-coordinate of 1/2? And let's see, it's got to be in between 0 and pi, because that is the range of the inverse cosine. And let me see here, I've got positive half here. So 60 degrees and pi over 3. I forgot to specify degrees of radians, so we'll put both. Yeah, 60 degrees for pi over 3 radians. Okay. So to kind of sum that up, check to see if you can cancel by looking at your inside function and then checking to see, does this number fall inside the domain? If yes, cancel out. If no, you can't cancel. And you have to start on the inside and work your way out slowly. Okay, I've got one more question for y'all. We're almost done, I promise. Lord knows I'm tired. I need one more clip. All right, y'all, last problem. Let's do it, let's do it. Okay. This is the big scary one. This is the big scary one. Okay. So it makes this one different from what came before. Before, all of my values, all my numbers, like the -3/4 is playing the role of it here, but the value of this before was actually on the unit circle. Now it's not. Now it's not, which is great. So I gotta use a slightly different method to go about figuring it out. And we're gonna do it with our good old friend, the triangles. Okay, so here's generally how you wanna do this. So step 1, so to speak, I'll say find the range of the, and here I'll try and match colors here, the inside function. So for us on that problem, my inside function is cosine inverse, okay? And again, not gonna make you memorize all these domains and ranges. These will be given to you on a test. The range of the cosine inverse is, let's see, 0 to pi. Okay. The reason I do this is because this tells me what quadrant I'm going to be in. It tells me what quadrant I'm going to be in. So this tells me what quadrant I'm in. It's not the only thing that determines it, but it helps. It gives me a visual way to imagine where this is going to be. Okay. So yeah, let's go ahead and draw that picture before I put step 2 here. So let me draw this picture here. All right. So I know the range of cosine inverse is 0 to pi, so it has to be between 0 to pi here. It can't be down here. Anywhere down there, it can't be. It's got to be quadrant 1 or quadrant 2. Okay? And then to get some more detail here, I need to do a little bit of math. I need a little bit of math. Okay, so I'm going to use this more, so just put this to the side for now. And let's look at step 2. All right, so I'm going to set the inside equal to theta, and then use right triangle trig. Okay, so that might sound a little complicated. It's not too bad, no problem. I'm gonna explain some motivation for this, like why this is even allowed at all. You may have noticed when we were doing all these problems that the answers to all of them, well, they're all numbers, obviously, but more specifically, they were all angle measures. They're all angle measures. And in fact, as long as your inverse trig function is defined, it's going to give you an angle measure, like always. By definition, that's what it's designed to do. That's why this here is a good idea. To say, okay, I don't know what angle this is, but I know if I were to evaluate it, it would be an angle, because that's like the whole point. So I set it equal to a variable, then I'm going to call my angle, then we'll solve a little puzzle, so to speak. Okay, so let's do it. My inside here is everything underlined in blue, so I'm just going to take theta, and I'm going to set that equal to the cosine inverse of minus 3/4. Okay? Now what I'm going to do is I'm going to take the cosine of both sides. So I have the cosine of theta equal to the cosine of the cosine inverse of negative 3/4. Okay, so I'm going to be a little hand wavy here. I know this problem has a solution, so I know it has to be possible to cancel here. But to be a little more specific, the inside bit is inverse cosine. The domain of that is -1 to 1, and -3/4 does fall inside that range. That domain, excuse me, goodness gracious. So I am good to go. I am allowed to cancel this out here, and so I find out that the cosine of theta is equal to -3/4. Oh, that's useful. That is very, very useful. I can use right triangle trig for this. But don't forget, cosine, it still is the good old adjacent over hypotenuse. And don't forget it either. This is coming from SOHCAHTOA. TOA. Right in here. Cosine is adjacent over hypotenuse. This is going to allow me to draw a triangle, solve for missing sides, and get all that good stuff. Okay, so let's draw my triangle here. We already talked about why it couldn't be down here. Has to be up here. And now I can eliminate quadrant 1. It can't be this. Since my adjacent side is negative, I have to end up going to the left. So we're going to have something like this. All right, and I'm real tired, y'all. Make sure I put these numbers in the right spot. Yeah, we're going to have theta here. My hypotenuse is definitely 4. -3 here for my adjacent side. This is my opposite side. And this is my hypotenuse. Again, I'm going to be a little hand wavy here. to be honest, I want to go home, I'm exhausted. You can solve for this missing side here with Pythagorean theorem. It's not the hypotenuse, so don't solve for C, solve for A or B. If you do that, you get that this missing side is the square root of 7. And then all I have to do is use right triangle trig rules for sine, okay? To really emphasize this point, this like why it works, I'm gonna recopy this. Inverse of -3/4, okay? Then I set this inside bit, I set that equal to theta, okay? So then I can replace all of this inside with the sine of theta. And once you look at that, that's why I drew a triangle. Because now I can just calculate the sine of theta. That's going to be opposite over hypotenuse. So it's going to be the square root of 7/4. And that will do it. Okay. That's all I've got for y'all today. So you are free to work on your assignment now. Naturally, I do not remember what it is, so let me look at that real quick. Let's see. Okay, that's going to be page 221. Let's see here. We've got 7 to 12. Yeah, 7 to 12. Then 21 to 32. Okay, so please work on this in class. This is not due Friday. This is going to be due well after your senior trip. There's a lot of problems. I'm not expecting to get this done. It honestly most likely will end up being due after our graphing trig functions test, because I want to focus on that first, then this. But please don't stress. I have no intention of just barreling through this and assuming you got it. I'll keep doing this until I make sure we got it and we understand. Okay, so it'll be due sometime way after senior break. Work on this for the rest of class. And that's a good place to stop.